Hello friends, in this session we will see how to find the solution to a state space equation. Let's begin. So now in order to find the solution to a state space equation, let us first try to write the state space equation. We know that the state space equation is given as x dot equal to ax plus bu and y equal to cx plus du. Am I right? Definitely. Right? This is what we have studied. Now if you see here, let me call this as equation 1 and let me call this as equation 2 for time being. Now if you see here, the first equation, which is this one, this equation 1, if you see, this equation is nothing but a first order linear differential equation, right? We also call it as FOLDE, first order linear differential equation. Why? Because say here you have this x dot, right? Because of this dot, which means it is definitely a first order differential equation, and since it is also linear at the same time, we can call it as a first order linear differential equation, FOLD. Okay, no problem. If you look at the second equation, what is the second equation about? So it is a algebraic equation. Now you please focus here. The main problem here is, if you see the main problem is, see, it is very easy to solve this algebraic equation, right? It is very easy, there is no problem. Yes, we can do that. But in order to solve this equation, this first one, x dot equal to s plus bu, which is also FOLDE, right? First order linear differential equation, it is very painful. Now the moment it is very painful, let us firstly focus on this equation. Let us try to find the solution of this equation. Now the moment I am able to find the solution of this equation, I will try to find the value of x of t from here. I will try to find this value of x of t from here, and then I can just simply replace it here, and then I can get the output y. Am I right? Yes. So now let us try to do so. Now see here, let me just take this x dot equal to ax plus bu aside, right? Now let us rearrange it. The moment I rearrange, it becomes x dot minus ax equal to bu, right? Now let me take two cases. What are those two cases? I will tell you, don't worry. Let me take the first case wherein I will keep this input as 0. Input is kept as 0. Input in the sense, what's the u, right? U is kept 0. And another case which is there, in which u will not be equal to 0, but that case we are not going to see for time being. Right now we will focus on this case only, when u is equal to 0. Now you please replace this u by 0. When you replace this u by 0, what do you get here is x dot minus ax equal to 0, because anything multiplied by 0 will give you 0. Is that right? Yes. Now in order to find, now if you just say here this x dot, right? What is this x dot? This x dot is nothing but dx by dt minus a into x, which is equal to 0, right? Now how to find the value of x? How to find the x, right? Now in order to find the value of x, the simplest thing that can be done is variable separable method. Before that, let me just take that ax on the another side, so let this become dx by dt equal to ax, right? Let me take it on another page, right? Yes. Now I need to use something called as variable separable method. In that method, if you see, yes, so we will take dx one side and we will take dt on other side, right? Yes. Now if you see here, this ax will also go to the LHS, right? Yes, so it also becomes 1 by ax into dx, which is equal to, and this dt goes there. That is what has happened here, right? Now what I am interested into, I am interested in the value of x. Yes, because I am trying to find the solution of the differential equation, so I am interested in the value of x. Now how to find that? Just simply integrate it. So let me just do that. Now let me integrate it from 0 to t. 0 to t. You may ask me that why I am integrating it from 0 to t. If you remember the first lecture, I told you that for control system we always need a fresh start, and that is the reason we always start from t equal to 0 to at some value t tending to t, whatever it can be, 2 seconds, 3 seconds, 5 seconds, 10 seconds. We are not at all interested in it, right? For us important is that yes, the limits are going to be from 0 to t, right? So we have applied those limits. Now let us solve that. So if you see here, 1 by a will be common, that will come out, and you will have integration of 1 by x dx from 0 to t, which is also equal to what? Yes, 0 to 2 integration dt will give you t, right? If I integrate this one, what do I get? I get 1 by a into ln of this integration. If I do, I get ln of x, right? Ln of x, this is also t. So here the limits you are going to apply is from 0 to t. So these are from 0 to t. Similarly, these limits are from 0 to t. Am I right? Yes. So what does that mean? In place of, because see here, this is ln of x, right? So you please take it. Yes, 1 by a into, yes, upper limit minus lower limit, which should be also equal to again upper limit minus lower limit. So what is the upper limit here? T. So you just replace it by t. The moment you replace it, it becomes ln of x of t. Ln of x of t. Am I right? Yes. Minus, what does it become? Ln of x naught, or we can say ln of x of 0, my, which is equal to t minus 0. Is that all right? Yes. So now if you just see here, therefore if I say here, let me just take this a on the RHS. Let me just take this a on the RHS. What do I get then? Yes, I get ln of x of t minus ln of x of 0, which is equal to a times t. Is that correct? Yes, definitely. Now, how to write this ln of x of t minus ln of x of 0? I will tell you. See here. We know that there is a formula. We have learned it in our 12th standard probably, that yes, ln of a by b is equal to ln of a minus of ln of b. Similarly, another formula also we know. What is that? Ln of a into b is nothing but ln of a plus ln of b. That is what we know. Now we have this kind of a thing over here. See, we have this kind of a thing over here, this black. So if you just compare, you find that this x of t is nothing but a, and this x of 0 is nothing but b. Is that right? Yes. So it is again similar to ln of a minus ln of b. So what happens to ln of a minus ln of b? In LHS, if you see, we will get ln of a by b. So what is a here? A is going to be x of t and b is going to be x of 0. So x of t upon x of 0. Is that correct? Yes, definitely. Now see here, which is equal to what? Which is equal to 80, which is given here, right? It is equal to 80. Is that correct? Yes. Now, now we know one more thing from our 12th standard basics. What is that? For example, if I have ln of x, right? Ln of x equal to y. Then if I want to find this value of x, then x will be nothing but equal to e to the power y. Or for that matter, if you know that if you have, let us say, log of x to the base a, which is equal to, let us say, y, then if I want to find this value of x, then it becomes a to the power y, right? So similarly, because it is ln in the sense, it is what? Log to the base e of x equal to y. So x is equal to e to the power y. That is what we know. So similarly, if I just apply it here, I will get, yes, what will I get? If I want to get this term out, then it will be x of t upon x of 0, which is equal to this ln. This goes e to the power at, e to the power at. Now student may feel that, sir, but this a It is a matrix. A is a matrix, right? But still, can this thing be applicable here? Yes, definitely. There is no problem. It will be applicable. How it will be applicable and how to find this e raised to 80? Trust me, I will tell you. Okay. Anyways, so this is x of t is equal to this. So if you just see here, let me just take it. Yes, x of t is equal to x of 0, or I can also call it as x naught into e to the power 80. This becomes your equation. Am I right? Yes. Now let us think of output. Now see, we are trying to find the output when the input is 0. I'm repeating, we are trying to find the output when the input is 0, right? Let us see. So we know that y is equal to what? Y is nothing but cx, right? So if I just, because it is cx plus du, now since u is 0, this whole term becomes 0. Now since this whole term becomes 0, y is equal to cx, so this need not be written, right? So now if y equal to cx, then it becomes y equal to c into x. What is this x? X is nothing but this x of t, which is nothing but x of 0 into e to the power 80. This is nothing but y. Now one very important thing, what is that? If you just see here this equation, this output, do you agree that this is the output equation? Yes. The moment it is output equation, which means that it is a response. It is a response, but it is a response when input is 0, because you just see here we kept input 0. Similarly, if you see, yes, here also we kept input as 0. What happens when input is non-zero? We will talk about that. Don't worry right now. Right now, my focus is when input is 0, what is my output? That's it. So, and yes, such equations are also called as, when you put your input to be equal to 0, such equations are also called as homogeneous equations. Homogeneous equations, right? Anyways, so this is nothing but the response, because we have y. Y is the output. So it is c into x naught into e to the power 80, right? So it is happening when my input is 0. That is the reason I will call it as zero input response. Also we call it as ZIR. In signals and systems we have studied that. It is called as zero input response. Through zero input response we can also try to find the stability. How it happens, I will tell you. But for time being, this is the thing. Right. Now, what is so special about e raised to 80? We will try to understand. See here. If you just keenly observe this equation, you understand that this particular, that yes, definitely x is the state. Yes, x is the state. So if my x is the state, now you just see, if x is the state, if you see from this equation, let me just come from this equation. If you just see, x is the state, yes, it is a state. What is the state? We have talked about it a lot. No need to explain it again. So if x is the state, if you see how my x state changes from its initial value to some value through a matrix, or I can say that how my initial value of state is changed from its initial value to some value via e raised to 80. Or I can also say that how the initial value of my state is transformed or transmitted from initial value to some value of t through some matrix e raised to 80. Hence this matrix e raised to 80 is also called as, phi of t, which is nothing but state transmission matrix. Or we also call it as state, because state is transferred from its initial condition to some value of at time. right? So it is called a state transmission matrix, or I can also call it as, state transition matrix. Both are right, and hence the short form that we give to it is nothing but STM, state transition matrix. STM. So this phi of t is nothing but STM. So see here, just because of this e raised to at, your state got changed from its initial condition at t equal to 0 to some value at t equal to t. Some value, right? So yes, so we have studied about the state transition matrix. It is also called as phi of at. Let me write it again. Yes. Phi of at is nothing but state transition matrix STM, which is nothing but e to the power at, right? Now our focus is to find the value of e to the power at, because we have understood now that's how important it is. Without this matrix your state cannot be transformed. That is what we have seen, right? So this matrix is very very important. Now the focus here is how to find the value of e raised to at. So in order to find the value of e raised to at, we have got three methods. We have got three methods. Let us see them. The first method that we have is called as useless method, or let me call it as method 1, which is called as power series method. Why it is useless, I will tell you. Don't worry. So if we expand, because see here, since it is in power of e raised to x, we can definitely expand it in terms of a Taylor series. Yes, Taylor series, definitely. So the moment if I can expand it in terms of Taylor series, which means I can write e raised to at as at plus a square t square upon 2 factorial plus a cube t cube upon 3 factorial plus a4 t4 upon 4 factorial, and so on. This will go up to infinity. This is not going to stop. Yes, definitely. Now what is the problem? What is the problem with this particular method? This particular method, the problem is, because see, since these numbers will go up to infinity, yes, so the moment these numbers go up to infinity, you may say that yes sir, because see, the moment this numerator goes to infinity, yes, definitely our denominator which is there, it will also go up to infinity somewhere. We don't know where infinity is. We don't know, but we know that yes, the number is very big number here divided by very big number here. So then yes, definitely it will get cancelled out. Yes. So you know what will you do is you will stop somewhere, because this expansion, you will stop somewhere where you might probably solve this one up to, let us say, here. You may solve here, no problem, right? Yes. But whatever answer you get here, whatever answer you get, will that answer be accurate? Will that answer be accurate? No. Why? Because there are some more extra terms as well, no? Yes, I know. After some time, some terms will become zero. I know that. But still, if you see, you will not get a completely accurate solution. Completely accurate solution. At the same time, it is very time consuming also. That is the reason I call this method as a useless method. So we are not going to discuss this particular method. We will be only focused on the exam. Why? Because we want the sums to be solved in a very very easy way, and that too accurately. So this method is none of our business, right? Then the next one which is there, because see, I just explained you this just to give you one overview that how this happens. If you want, you can deal that. How? You please refer your mathematics, there is no problem. If you want, you can do that, but for me personally, yes, this is a very useless method which should not be used, right? Anyways, let us think of method 2. If you think of method 2, method 2 is going to be inverse Laplace transform method. Inverse Laplace transform method. Right, this method is very important method. Put some star marks or something here. This is a very important method, very important and useful as well, and very useful method also. In exams, most of the times we will be using this particular method only. Don't worry. How to solve those problems? Believe me, I will tell you. Okay. Anyways, what is the third and the last one? Method 3. Method 3 is nothing but Cayley Hamilton method. What is that method? We will talk, don't worry. So we will be basically dealing with these two methods only: inverse Laplace transform method and Cayley Hamilton method, right? Now, if you see here, for this particular video, this particular session, my focus will be only on this method 2. I will be only talking about this method 2. We will have a derivation as well, and we will enjoy the video. About this method 3, we will talk in the next video for sure. But for now, I am going to focus on this inverse Laplace transform method. Okay? Yes. Now see here. Yes. So far we have seen that x dot equal to x plus bu, right? And since we are talking about homogeneous solutions, we put u equal to 0. Input is made 0, right? So it becomes x dot equal to ax. Yes, there is no problem. We know that. Now, what is inverse Laplace transform method? You may say, sir, it is already in time domain. No, yes, it is in time domain. Then why you are again going to do some stuff like inverse Laplace and all? The reason is, I will tell you. The reason is because this is not x, this is x dot. That is the only reason. I want it in terms of x. I don't want any differential term here. That's the question. I don't want any of the differential terms, which means this has to be replaced in some or the other way. So let us apply Laplace transform now. Yes. So if you apply Laplace transform, you get, yes, since it is x dot, which means it is dx by dt. So for dx by dt, the Laplace transform is going to be what? It is going to be s into x of s. So yes, definitely you may write here s into x of s, which is equal to a into x of s, right? Yes, because if x of t has a Laplace of x of s, then this is going to be true. If you remember, when we tried to find transfer function out of a state space model, right, we did not consider initial conditions. Yes, we did not, right? But here if you see, we have to consider the initial conditions as well. Here we have to consider the initial conditions as well. Why? Because it is a differential term, and if at all there are any initial conditions, then those have to be considered. Why? Because we are not talking about transfer function. We are not talking about transfer function. We are talking about solution. Anyway, so because what happens here is, student just say that yes, it is going to be s into x of s equal to s. So just give this si minus a, right? Si minus a into x of s, and this data equal to 0. So x is going to be 0. Will that happen? No. That is the reason initial condition is very important. Yes, if initial condition goes 0, we will see what happens then. But for time being, this is very important, right? So let me erase this. So yes, definitely initial conditions has to be considered. So here it becomes minus x of 0, right? Yes. Now let us take x of s on one side and x naught on the another side. So we get here s into x of s minus a into x of s, which is equal to x naught, or we can say x of 0, which means value of that particular state x at t equals to 0. That is what is the meaning of x naught. Anyways, let us focus here. Yes. Now you please see, how will I write this? I see that x of s is common. I just put it here. So here what I have is s minus a. Now if you see here, this a is a matrix and this s is the number. it just cannot be compatible with each other. That is the reason this S has to be converted into a matrix. So in order to convert it into a matrix, what we put is S into I minus A into X of S, which is equal to X naught, right? By the way, these X are all capital, right? Now see here. Yes. But am I interested in this Si minus A? No. I somehow want to eliminate this one. Why? Because I want X of S in terms of X naught. Why? Because my aim is to find X of T. So it can only happen if I have X of S. Because if I have X of S, I can directly apply inverse Laplace transform. Right. So I just don't want this one. So if I don't want this one, there is a method called as, which we have talked about earlier as well, right? It is called as left cancellation method. What do we do here? Yeah? Yes, we do pre-multiply by, because you have to do it from the left, so it is going to be pre-multiply, because you start from here, right? So it is pre-multiply by Si minus A inverse, right? So if I just pre-multiply by that, what happens? Because now when I'm pre-multiplying by this, is that so that I should only pre-multiply on the LHS? No, at the same time I have to also pre-multiply on the RHS as well, such that the effect is cancelled. Yes, definitely, right? So on both sides is very important, right? Yes, so definitely you will be pre-multiplying by Si minus A inverse, right? Yes, Si minus A inverse. And what you have here? Yeah? Yes, you have here Si minus A multiplied by X of S, which is equal to, yes, definitely you have this X of 0, and you have this Si minus A inverse. You have this Si minus A inverse, right? Now, if you see here, these both will get cancelled, because A into A inverse is nothing but I. So yes, definitely these two will go, because their multiplication will give you I, and I is nothing but unit matrix, which is 1. So that is fine, right? So it becomes X of S equal to this one. So what do I get here is, yes, so what do I get here is X of S is equal to Si minus A inverse into X naught, or X of 0. Did you get this? Yes. Now what I want X of T, right? So let us apply Laplace inverse. So by applying inverse Laplace transform, right, what do I get here is Laplace inverse of X of S is nothing but equal to Laplace inverse of Si minus A inverse into X of 0, right? So now how to find this X of S? How to find this X of S? Very simple. This Laplace inverse of X of S, it is nothing but X of T. So it is nothing but X of T, which is equal to Laplace inverse of Si minus A inverse into X of 0. Note that what happens is, when people take this inverse Laplace, they just put inverse here, but they do not put inverse here. So you have to remember that yes, you have to put inverse there also. I am telling you this, what mistake students do in exam, right? This is the equation. Now if you remember the previous equation which we had got, the general equation, right? Yes. So this was our general equation, right? This was the general equation. This black, I'm making star, right? This was the general equation. What is that equation? X of t equal to X naught into e to the power 80. So it is nothing but, right? Yes, definitely. So now you just see here, I will tell you, don't worry, don't worry. Yes, if you just see here, when you apply Laplace inverse to this X of 0, will there be any change in that? No, because it is already in time. It is basically a constant. This is a constant, right? Because it is the value of that state at t equals to 0. That is nothing but a constant. So this bracket is going to only come here. So basically, if you see, just compare, it becomes Laplace inverse of si minus a inverse into x of 0, which is nothing but x of t, if you think of this equation here, right? Because this x of t is just a constant and it will come out of that bracket. Yes. So now if you compare these two equations, what do you get? Yes, x naught are same. The only thing is that e raised to at is nothing but Laplace inverse of si minus a inverse. So from this, what you understand is that e to the power at is nothing but equal to Laplace inverse of si minus a inverse. This is nothing but STM, state transition matrix. I hope you are understanding this point. So from now in our Laplace transform approach, if you see, it is going to be e to the power at is nothing but Laplace inverse of si minus a inverse. Don't forget to take the inverse of si minus a. That is very, very important. Now if I'm talking so much about it, let us take one example. So example 1. Yes. So now what are they asking? They are asking that please find the STM. STM is what? A state transition matrix. Because many of the times in exam also they may not mention that it is state transition matrix. They may just say that please think of STM. Anyways, so yes, and next is what? Solution of output, which means we want the value of y. Yes, and I can understand that. But yes, in order to find the value of y, you need to get the value of x also. So how to get that value of x? We know that x of t is equal to what? X naught into e to the power at, which is nothing but state transition matrix. So see here, because we know that to get x of t, you always do the reverse engineering. Believe me, it works. You want this y, right, and you want it when input is 0. No problem, input is 0 means homogeneous equation. Our case, yes, no problem. So x of t is nothing but what? X naught into e to the power at, for that matter. Am I right? Or to be specific, because this order should not be changed, right? So you can also do that. Anyways, right? So now just see here, or to just change this, let me just keep it this way, because the order should not be changed, right? Because matrix multiplication is not cumulative, we know that. So it is going to become e to the power at into x naught. You will get the real feel of e raised to 80 now. Don't worry, you will understand that, and at the end we will draw a very beautiful observation out of it. You will love it. Anyways, x of t equal to e to the power into x naught. Yes, we know that. Is x naught given? Yes, x naught is given. Yes, x naught is given. Is e to the power 80 given? No, that we have to find. And what is that? That is state transition matrix. In order to find state transition matrix, what you need? You just need Laplace inverse of si minus a inverse. That's it. So do you have a? Yes, you have this a. You know that since it is x dot into ax, so this has to be a. This matrix is going to be a. So you have got a. You just need to find si minus a inverse. You just need to find Laplace inverse of si minus a inverse. You just follow the steps. Anyways, let us do that. See here. So si minus a inverse. Let me think of si minus a first. What is s into I? Is nothing but s0 0s. Right. What is minus? Minus a. What is a? 0 1 minus 2 minus 3. Right. If I just put them together, what do I get is s minus 0 is s, 0 minus 1 is minus 1, 0 plus 2 is 2, and s minus of minus 3 is going to be minus into minus plus, so it becomes s plus 3. Is that correct? Yes, that is all si minus a. Now I want si minus a inverse. So if you see here, what is si minus a inverse? Si minus a inverse is nothing but adjoint of si minus a. See, since it is just starting, I will do it very, very slow, but at the end we can go fast, no problem. And divided by determinant of Si minus A. We have seen that already. So what is adjoint of 2 by 2 matrix? What is adjoint of 2 by 2 matrix? We know that. See here, let us think of the shortcut once again. See, what we do, we just flip this diagonal elements and we change the sign of this off diagonal elements. That's it. So if this is the diagonal, this is only the diagonal, right? So you just flip it. So this becomes S plus 3 and this becomes S. And you please change the sign. Change the sign. Here also change the sign, right? So it becomes minus 1 becomes plus 1 and this 2 becomes minus 2. That's all. This is adjoint. Yes. Divided by what? Divided by, or I can say multiplied by 1 upon, yes, nothing but equal to 1 upon, yes, Si minus A determinant. How to find a determinant of this one? Si minus A is here. So how to find a determinant? This into this minus this into this. So it becomes S into S plus 3 minus 1 into 2. So at the end what you get here is nothing but 1 by S square plus 3S plus 2 into S plus 3 1 minus 2 S. Is that right? Yes. Now what are we supposed to find next? We need to find Laplace inverse. So what if I just place this term inside? So before placing this term inside, can I factorize it? Yes. So if I can factorize it, what are the factors of this one? What do I get here factors? I will get S plus 1 into S plus 2. So if I just rewrite this, I get, right? Yes. Now if I just place this denominator inside, means if I divide by this two factors to each and every number, right? So it just becomes, this way, that S plus 3 upon S plus 1 into S plus 2, this becomes 1 upon S plus 1 into S plus 2, this becomes minus 2 upon S plus 1 into S plus 2, and this becomes S upon S plus 1 into S plus 2. This is the equation we have got, right? So this is nothing but Laplace of Si minus A inverse. Now what we want is, we need to take the Laplace inverse. So if you want to take the Laplace inverse, which means you need to apply partial fraction methods here. Why? Because if you individually have 1 upon S plus 1, you can solve it. If you individually have 1 upon S plus 2, you can solve it. But if you have them in multiplication, you cannot solve it. Why? Because Laplace is a linear operator. Laplace is a linear operator. It separates itself whenever there is addition and subtraction, right? So since if you say here we have multiplication, here we have multiplication, it just cannot happen, so we need to apply partial fraction methods. Let us apply them and see what happens. So how to find partial fractions here? Yes, it is going to be a upon S plus 1 plus b upon S plus 2, a upon S plus 1 plus b upon S plus 2. Similarly, for this third term, a upon S plus 1 plus b upon S plus 2. Similarly, for the last term, a upon S plus 1 plus b upon S plus 2. Is that correct? Yes. Now, how to find Laplace? See, basically what you need here is a and b values, means a b a b a b a b. How to find those values? We have already seen that. Let me just explain it to you one more time in detail. Next time I will ignore that part, but for time being, bear with me please. So let me call this as the first term, this as second term, first term, second, or I can say here first term, second term, third term, and fourth term. Let us simply find them. So let us think of first term. What is the first term? It is going to be s plus 3 upon s plus 1 into s plus 2. So, right, we have seen that this can be represented as a upon s plus 1 plus b upon s plus 2. Right. Now, to find the value of a, how to find the value of a? You please write the whole LHS. You please write the whole LHS. What is the LHS? S plus 3 upon s plus 1 into s plus 2. Except what is there below a? Below I am going to have s plus 1, so s plus 1 has to be ignored. That's it. And what you have to place? You have to place, you please equate this to 0. S plus 1 equal to 0. What you get is s equal to minus 1. So you please put it here, s equal to minus 1. So if you replace here, what you get is, so if you replace here, what you get is, in place of s, if you put minus 1, you get minus 1 plus 3 upon minus 1 plus 2. Is that correct? Yes. So it is equal to what here? Yes, it is going to be minus 1 plus 3 is 2 divided by minus 1 plus 2 is 1. So it becomes 2. So you can find a is equal to 2. Right. Similarly, how to find b here? Yes, b is equal to what? B is nothing but, please write the whole LHS again one more time. What is the whole LHS? S plus 3 divided by s plus 1 into s plus 2. Then except what? Except what is there below b? So below b I have s plus 2, so let me just simply cancel it. I am not going to consider it in this equation. So at s equal to what? Just replace this by 0. So s plus 2 equal to 0. We get s equal to minus 2. So you please put here s equal to minus 2. Is that right? So if I equate this, I get minus 2 plus 3. In place of s, if I put minus 2, I get again minus 2 plus 1. So what do I get here is, yes, I get here 1 minus 2 plus 3 is nothing but 1, 1 upon minus 1, therefore b is nothing but minus 1. I hope it is clear. Now a and b are formed, so this first term can be written as what? First term can be written as yes, 2 upon, because a is equal to 2, so 2 upon s plus 1 plus b, what is b? Minus 1, so minus 1 upon s plus 2. This is the first term. Let us find the second term. If you see here, the second term is what? 1 upon s plus 1 into s plus 2. Right. So let me just equate it. So yes, definitely this can be written as a upon s plus 1 plus b upon s plus 2. Now you will do it fast, right? Yes. If I want to find value of a, what do? I write the whole LHS. What is the whole LHS? 1 upon s plus 1 into s plus 2. Now, whatever is that below a, I just simply ignore that. I have ignored that. Now, I will equate this to 0. So, I get s plus 1 equal to 0. So, s is equal to minus 1. So, I just put here s equal to minus 1. The moment I put here, I get 1 upon minus 1 plus 2, which is nothing but 1 upon 1. Therefore, a is nothing but equal to 1. Simple. Now let us try to find b. If I think of b, b will be equal to what here? Yes, write the whole LHS. 1 upon s plus 1 into s plus 2. Except what is there below b? Below b I have s plus 2. So you please ignore that. Now this you have to equate at s equal to what? So s plus 2 is equal to 0. Therefore you get s equal to minus 2. So you have to equate this at s equal to minus 2. So you please put there 1 upon minus 2 plus 1. It becomes 1 upon minus 1. Therefore b is nothing but equal to minus 1. Is that correct? Yes. So term 2 can be written as what? Term 2 can be written as 1 upon s plus 1 minus 1 upon s plus 2, because a is 1, b is minus 1. Is that correct? Yes, definitely. Now let us think of the third term. The third term, if you see, It is going to be this one. This is the third term. So it is minus 2 upon s plus 1 into s plus 2. Am I right? Yes. So if I equate these two again, a upon s plus 1 plus b upon s plus 2. How to find that? Now things will become very simple for you. How to find a? Yes, a is nothing but, yes, write the whole LHS except what is there below s a. So it is going to be minus 2 upon, below a I have s plus 1, so I will just ignore that and I will write the remaining term, which is s plus 2. At what? Yes, definitely equate this to 0. So s plus 1 equal to 0, I get s equal to minus 1. So you please put s equal to minus 1 here. So it becomes minus 2 upon, at s I put minus 1, so it becomes minus 1 plus 2, which is nothing but minus 2 upon 1, which is nothing but minus 2. So I get value of a to be equal to minus 2. Is that all right? Yes. Now let us try to find value of b. What is b here? B will be equal to what? B will be equal to what? Yes, write the whole LHS, so it becomes minus 2 upon, but except what is there below b. Below b I have s plus 2, so I am just going to ignore this s plus 2 and I will write only s plus 1. Now see, things are becoming very faster. So now it becomes, see, s plus 2 equal to 0, therefore s is equal to minus 2. So if I just put s equal to minus 2, what do I get here is minus 2 upon minus 2 plus 1, which is equal to what? Minus 2 upon minus 1, therefore which is equal to 1. So a is equal to, this is equal to 2, I'm so sorry. So a is equal to 2. Sorry, b is equal to 2. This is b, I'm so sorry, this is b equal to 2. Right. Now how to find? So the third term can be written as either you can say this one as, let me take this term first. So I can do that, no, because a plus b is same as b plus a. How does that matter? So let me just take it as 2 upon s plus 2 minus 2 upon, what do you say, s plus 1. Is that correct? Yes, no problem. Right? So this is the third term. Let us think of the fourth term now. Yes, so if I think of the fourth term, what is that fourth term? Yes, this is the fourth term, s upon s plus 1 into s plus 2. Am I right? Yes. Now how to find that again? It is very simple. See, this can be made equal to a upon s plus 1. You may say that, sir, these things are becoming very tedious for us. How? No, these are very simple. Right? Why? Because see, I will tell you, since it is a starting for you, you might feel a bit this thing, but it is very easy. Anyways, so this becomes s plus 1 to s plus 2. Right? How to find a here? Very simple. To find a, write the whole LHS. What is that? S upon, except whatever is there below a. Below a I have s plus 1, so I will ignore s plus 1, I will only write s plus 2. At what? S equal to minus 1. How you got this? By equating it to 0. S plus 1 equal to 0, so s equal to minus 1. Right? So it becomes minus 1 upon minus 1 plus 2. Therefore this becomes what? Minus 1 upon minus 1 plus 2 becomes minus 1 upon 1. Therefore you get value of a as a equal to minus 1. Is that correct? Yes. Right. Similarly, if I think of b, how to find b? Yes, write the complete LHS except what is there below b. Below b I have s plus 2, so I am going to ignore s plus 2. So I get s upon s plus 1 at what? S equal to what? S plus 2 equal to 0. If I put, then I get s equal to minus 2. So for that I will equate this, so I get minus 2. Now let me just put it, minus 2 upon, yes, minus 2 plus 1. What do I get here is, yes, I get b equal to how much? I get this one as minus 2 upon minus 1. Therefore b is equal to 2. Let me take b first, so I can replace this fourth one. I can also show it as, yes, I can if I keep this b first, then I will get 2 upon, yes, b upon s plus 2. So 2 upon s plus 2 plus, what is this? Yes, a upon s plus 1, so minus 1. So let me just put minus 1 upon s plus 1. Is that correct? Yes, definitely. Now let us keep everything in that matrix. So that matrix, if you see, Si minus A inverse matrix, if you see, that matrix is going to have these terms. This is the first term, 2 upon s plus 1 minus 1 upon s plus 2. Then the second term is 1 upon s plus 1 minus 1 upon s plus 2. Then the third term we have is 2 upon s plus 2 minus 2 upon s plus 1. Right. And the last one is going to be 2 upon s plus 2 minus 1 upon s plus 1. This is the matrix. But is this our intention? No. Our intention is to find Laplace inverse. So Laplace inverse of this, Laplace inverse of this. So you please apply Laplace inverse to each and every term inside it. Each and every term inside this. So if you apply Laplace inverse, what do you get here is, what do you get here? Yes, 2 upon s plus 1 is nothing but 2 into e to the power minus t. See, now I am not here to teach you inverse Laplace, right? See, we have already seen that many times. So this is not the time to, learn this. You must be knowing them to the best of your knowledge. Anyways, so it becomes 2 into e to the power minus t minus, yes, e to the power minus 2t. Then yes, again this becomes e to the power minus t minus e to the power minus 2t, right? Again this becomes 2 times e to the power minus 2t minus 2 times e to the power minus t, right? And this becomes, yes, 2 times e to the power minus 2t minus e to the power t. So this becomes your Laplace inverse of Si minus A. What is this equal to? This is nothing but e raised to at only, or we also call it as STM. Is that correct? Yes. Now, what is important for me, because I have extended this question right to the solution of output equation. I have only got STM. Now I need x of t. How will I get x of t? Because see, x naught is given, x of 0 is given. See, just imagine if x of 0 was 0, then if x of 0 was 0, then even if you have this STM, no, it is of no use, because x of t will be 0. Why? Because x of t is equal to e to the power at into x naught. So if you just see here, we know that x of t is equal to e to the power at into x naught, right? What is this? What is e to the power at? We have seen that it is going to be, right, into x naught. What is x naught? X naught is 0 1, which is given. See, x naught is given 0 1, right? You please just replace that. So what do you find here is x of t equal to, what do you find is, yes, row by column, right? So this row into this column, what do you get? What do you get? This into this become, this into this becomes 0, and this into this is what you get. So you get e to the power minus t minus e to the power minus 2t. Similarly, this row multiplied by this column, what do you get? Yes, this into this 0 becomes 0, and this term into this 1 is what you get. So you get here 2 times e to the power minus 2t minus e to the power minus t, right? Now, are you supposed to find x of t? No, my intention is to find y of t. For that, I need x of t. My aim, my destination is to find y of t. So let me simply find y of t. So y of t is nothing but what? Y of t is nothing but, yes, we have seen that it is c into x of t. Y is equal to cx. We know that cx plus du, but u is equal to 0. So there is no implication of that matrix, right? So c into x of t. Is there c given? Yes, c is given. What is c? 1 0. If you see here, c matrix is given, which is 1 0. So this particular c multiplied by this x, what is this x? This is the x. E to the power minus t minus e to the power minus 2t upon 2 times e to the power minus 2t minus e to the power minus t. This is the thing. So what do you happen? Yes, this row multiplied by this column. this into this, you will get e to the power minus t, right? You get e to the power minus t, right? Then again, yes, this row multiplied by this column. What do you get here? You get 1 into this, you get this 1 multiplied by this first one, you get minus e to the power minus 2t. Therefore this is nothing but your y of t, also called as zero input response. Now here you have to make some observations. What do you understand from this? See, even this zero input response tells you that the poles are minus 1 and minus 2. This tells you that the poles are minus 1 and minus 2. Yeah, nothing but one only, no? So here you get that yes, poles are minus 1 comma minus 2. So if you see the same poles we had got here, the same poles we had got here down, if you see, let me change the color. Here if you see the same poles I had got s plus 1 into s plus 2. Is that correct? Right, right. And another thing, if you see, me see here, the same poles I got when I found out the determinant of si minus a, right? And another thing, if you see, another thing, if you see, you please tell me, is this stable? Yes, it is stable. Why? Because both these quantities, if you see, let me just change. Yes, both these quantities, if you see, e to the power minus t minus e to the power minus 2t, both these quantities, if you see, these quantities are going to tend to 0. After some time these are going to become 0. Am I right? Yes. So the moment these terms become 0, what does that mean? Yes, because see, input is not given, 0 input response. If input is not given and at t tends to infinity, if my system response is 0, that means it is a stable system. Just imagine that you have not given the input, but still you have some output of the system. Then just imagine, you will be scared. You will see that there is some or the other thing inside it. You may get that particular feeling of, some ghost or something. Because just see, input is not given, still the system gives you the output. What does that mean? Some sort of conjuring, right? Anyways, just I'm joking, this just yes. So this is the whole thing. So yes, we have understood that it is a stable system. How do you understand that? When you find this, also you can understand this stability by si minus a determinant, right? So that's all for time being, because Laplace transform approach is done. The next session we will be talking about third method, which is nothing but Cayley Hamilton method. Thank you.